Hello. In this video, we are continuing with calculations using the equilibrium constant, the Kc. So I will show you some examples and then you will work on some exercises that you need to do to understand how to use the equilibrium constant calculations. So this is the first example. 1 mole of hydrogen gas and 1 mole of iodine vapor are introduced into a 5-liter sealed flask, and this mixture is heated until equilibrium is established. So that is the equation: H2 gas, I2 gas to 2 HI gas. So first thing that you need to do is look at the equation, look at the coefficients of the reactants and products. So at equilibrium, the mixture is found to contain 1.580 mole of HI, and then we want to determine the concentrations of hydrogen, iodine, and the HI or hydroiodic acid at equilibrium. And we also need to be able to calculate the equilibrium constant of this reaction. So before you think about calculations, you need to know that the equilibrium constant is calculated using a concentration, not number of moles. So what you want to do, the first thing is to change this into molarity from the number of moles. Now, how do we solve this problem? As I said previously, you need to change the moles given to the number of moles, but we should take note that the volume that we are given is 5 liters. So that is our volume, and we know the molarity is given by the number of moles over volume in liters. So we already have our volume, which is 5 liters. But we also have our equation. The equation is very important in determining the Kc, because the expression of Kc depends on the stoichiometry of the equation. Now, first, we need to know that we have 1 mole. If we can come back here say 1 mole of hydrogen, 1 mole of iodine. So if we go back here, we have 1 mole of hydrogen, 1 mole of iodine, but we need to change it to the concentration. So what is the concentration of 1 mole of hydrogen in 5 liters? The concentration is given by the mole per volume, which is 1 mole per 5 liters. So both hydrogen and iodine have a molar concentration of 0.200 mole per liter, or just 0.200 molar. So these two have a concentration of 0.200 molar each. What about the HI? we know that the number of moles of HI at equilibrium was 1.580 mole. But now you need to turn that into concentration. So it's number of moles per liter. So your calculation here gives you 0.316 molar. So we now have what we can call initial concentrations for these two, for hydrogen and iodine. That is concentration before equilibrium. But now we have the final concentration, that is the equilibrium concentration for HI. So the question is, how do we proceed from there? So let's check the next slide. Normally what we do is we have our equation here. If I can put the equation in the table, so I put the equation in the table, and then I go step by step. What is my initial concentration of reactants? What about initial concentration of products? So we know that we have 0.2 molar of hydrogen, we have 0.2 molar of iodine. But before the reaction, we didn't have any product because the product was not there. So the concentration of the product is 0.00 molar. Now, what is the change in concentration? The change in concentration will be given by this. So our calculations found that the concentration of HI at equilibrium was 0.316. That's the change in concentration. But how do we get the concentrations in here? Look at the stoichiometry. Here we have 2 of HI, while here we have 1 of this, here we have 1 of this. So what it means is that for every 2 molar of this one, there is 1 molar of this, there is 1 molar of this. So if the change here is 3.316, which is we added 0.316 of HI, which means we used up this one but over 2 for this one. So half of this is used up for iodine and half of this also is used up for hydrogen, because the ratios between hydrogen and HI are 1 to 2. The ratios between iodine and HI are 1 to 2. So this should be double and this should be single. On the reactant side, we need to, because we are using it up, so we are subtracting. Initial, we subtract to get our final concentration. The same thing, initial, we subtract to get our final concentration. Here, initial, we add to get our final concentration. So these are our equilibrium concentration. That is, the concentrations at equilibrium are 0.042 for hydrogen, 0.042 for iodine, and 0.316 for 2 for HI. Now from here, that's when we go back to use our equation. We go to use the expression for KC. So let me stop here to get to another video. So here we have our initial concentrations, we have change in concentration, and then we have equilibrium concentrations here. So what's the next step from here? The next step is to write down the equilibrium expression, Kc. So from the equation, we see that here the coefficient is 1, the coefficient is 1, and the coefficient is 2. So we say that the reactants should be the denominator, and the products should be the numerator. So the products are on the top, at the top, the reactants are at the bottom. So when you get your equilibrium expression, now you substitute with numbers, you plug in the numbers. We know from here we have 0.316 as our product, but squared, and we have 0.402 as one product and 0.402 another product. So because they are the same number, we just square them. Instead of saying 0.042 times 0.042, we just square them to get the equilibrium constant, which is Kc. Another way to look at this is if we write our equation again, is that we have our initial concentrations here, and if we let the change in concentration be x, so the concentration of H will change by minus x or negative x, because we are consuming hydrogen. The same, the concentration of this one will also change by negative x, because we are consuming hydrogen. So we have these x's because the coefficient here is 1, the coefficient here is 1. But now look at the product. The coefficient of the hydroiodic acid is 2. Therefore, the change in concentration here should be 2x. So our x's, the way we write them, depends on the coefficient we are dealing with. So any like 1 mole that we consume here, we are going to produce 2 moles on this side. Any 1 mole we consume here, we are going to produce 2 moles on this side. Or 1 molar we consume here, we produce 2 molar of this one. 1 molar we consume here, we produce 2 molar of this one. So our equilibrium concentration can be given by 0.200 minus x, 0.200 minus x for the reactants, and then 0.00 plus 2x, or it's just 2x for the products. So from here, that's how we can now work on trying to figure out what to do with these x's that we are given.